So this is supposed to be an unstructured section. And so I figured what I would do is try to say some hopefully somewhat provocative things for a few minutes about the state of cosmology, and then open this up to discussion on where do we go next. And, Shirley assigned me this topic of post-pandemic cosmology, and I wasn't quite sure what that meant. One of the nice things about cosmology is we operate on time scales that are long compared even to the seemingly far too long time scale of the pandemic. But let me just, sort of begin by sort of invoking the Rumsfeld doctrine, which says if you don't know how to solve a problem, you make it bigger. So I'll make this bigger and then just post-pandemic cosmology and try to just look at where we are overall and start with a rather long arc. And I'll take a perspective of just my own experience in cosmology starting in the 1980s and how we got to where we are now. And I think some interesting lessons from the early 80s that I think are quite relevant to where we are at the moment. So when I took a class from Jim Peebles, and he talked about cosmology in 1981, we talked a lot about the flatness problem. Was omega 1, was it less than 1? And why was it so close to 1? Why was it so close to an unstable fixed point? At that point, there was very compelling evidence for the existence of dark matter, though we did not know what dark matter was. And most of my astronomer colleagues were convinced it was low mass stars, right? This is really, the sensible thing to do. They've just evaded detection. We will have better infrared sensitivity in the 80s, and we will see these low mass stars. And what happened in the early 80s, and I feel some of this at the moment with interactions between machine learning and physics, was there was a tremendous flux of ideas and people from particle physics that really changed the field. It brought along ideas like inflation. It brought along ideas like non-baryonic dark matter. People like Ed Witten, John Ellis showed that supersymmetric models could easily produce non-baryonic dark matter. This stimulated a lot of work by astrophysicists. Once you posit non-baryonic dark matter, that led to simulations of dark matter evolution, cosmological evolution, the sort of Davis, Estopiou, Frank White papers that opened up the whole field of cosmological simulation. Work out of the Santa Cruz group, Blumenthal, Faber, Premack, and Rees, and others sort of gave us a paradigm of dark matter formation in a universe in which it was dominated, and that really shaped a lot of the ideas and the framework under which we're still operating. And the subsequent 30 years was a period of tremendous observational and experimental progress that followed those theoretical advances. And observations of large-scale structure, the cosmic microwave background, and supernova really led to the establishment of the lambda CDM standard model, which has proved remarkably successful. The data keeps improving, and it fits really well. And where are we now? Well, I would argue we now are in a state of cosmological crisis. And I'd say the crisis is not because of the observations of the Hubble constant. Those, I suspect, most likely will turn out to be due to measurements errors in the Cepheids, if I were to place a bet. We'll see. I think this is something where observations will solve the problem. We'll see. One of the many things I'm looking forward to from the James Webb Space Telescope is improved observations of tip of the red giant branch stars, which will give us an independent measurement of the Hubble constant at high precision, and we'll either show it's a problem, which will be most exciting, right, and that will suggest new physics, or we'll show that there's some systematic we missed in the Soviets. So what do I think is the cosmological crisis? I think the crisis is a lack of focus on big ideas. I think the crisis has been a lack of new ideas, lack of focus on the big questions like what is dark matter, what's dark energy, is there evidence for new physics, how do we model and understand multi-scale physics? You know, we need to do that in order to make real progress. And you know, how do we learn new physics and get a deeper understanding from data and statistical tools? And you know, one advantage of being foundation president now is I don't have to worry about grants, so I can say I blame the observers for this. Basically, it's observers sitting on review committees and grants committees that really want people to do theory that's too focused on interpreting and getting a slightly better fit to the next set of data. You know, I am so bored by covariance matrices. You know, I computed them a long time ago. We did them. It's just a technical problem, and it's not. You know, and the fact that too much in the way of jobs and grants and things are driven by encouraging people to make incremental progress. And I think what we need is new ideas and new directions. And, you know, to me, one of the excitements of a meeting like this is, and the importance in some ways of meetings, is to bring together people with different perspectives to learn from each other and think. Because by thinking about things in new ways and asking a new set of questions, that's really how fields advance. And you know, then if I were to, you know, go to my assigned topic of pandemic problems, I think the problem with pandemic is work from home, which I think is intellectually terrible. I think it's a great way to write more code. It's a great way to keep doing what you've been doing before. A lot of companies that, you know, was talking with my brother-in-law who runs an insurance small business of 10 people. And the part of the business which is processing paper and doing the same thing over and over again is now being done remotely from the Philippines. They've hired something, they've offshored it. You can paste, and then the parts of the job that require talking to new people and doing new things, you do in person. And I'm really glad people are here because I think the novel ideas require intellectual stimulation. Real theoretical advances are not going to happen from home. You can go home and quietly do work, and that's important. And, you know, sitting down and doing a calculation or writing code is essential. Yeah, I think the way for post-pandemic cosmology to advance is for everyone to get vaccinated, come to meetings, talk to new people, and focus on big problems. So that's my provocative opening statement. And I'm not sure what format we want with this, whether we want to just, you know, this is a discussion, and I try, so I just encourage everyone, remember to hit the button and to just say what you think we should be doing in cosmology and see where we go. I'm actually going to sit down and encourage people to just say what comes to mind.
Yeah, so first of all, I want to address something that you said regarding the lack of focus of big ideas, and I fully agree. However, the ideas that you cited are already out there. right? So we wanna bring the so-called unknowns, unknown unknowns, right? So it's, whatever it is that we think we know, it's probably not that, right? And then I think I agree with you that the bigger problem is actually the structure of how science is done for the last 20 years or so, right? So the metrics in which science people are measured are the number of articles, maybe the quality of articles, but really no one ever reads those in depth. The only people who read those are the reviewers, if you're lucky, right? And so it goes to credentialism, right? Where you did your master's, where you did your PhD, who did you postdoc under, what journals did you publish in, and that is in no way guarantees originality or even quality. It's a pseudo metric that is ill sufficient, right? And so I think with trying to be as meek as I can, we really need to change the structure of academic. And you guys, I think Flatiron, I don't want to kiss up too much, right? But I think Flatiron is doing something correctly with the fiscal structure that you have here. That, as far as I understand, right, that researchers don't have to be worried all the time where their next paychecks come from, and in the larger context, there's a go get it attitude, right? You want to do this, you want to do that. That sounds fun. That sounds fine. Go do it. We have your back. We got your resources. And I think that academy as a whole has just is just fermenting at this point, with a few notable exceptions,
So how
personal exceptions.
How would you change it?
How would I change it? It's hard, and I talked about it with Shirley, I think, if she's here. But hi. But first off, I promise you, in 10 years, there's going to be a Flatiron in Israel. That's my promise to you, right? With a different fiscal structure, because you guys have great donors, right? But in Israel, you can't have that. You want to have an institute who is fiscally independent, right? The government can't tell it what to research or not. Donors can't tell it what to research or not, and it has to have good ties, very, very good ties with the industry, such that you can outsource intellectual and put a price tag on that, right? And so you get income. But that's work in progress. I need to think about it some more. But that's where I'm going with this. And I think also, if I may look at just the other end of the rainbow in terms of not science but humanities, right, which are as essential as sciences in my view, right? Humanities are really in a bad place right now. There's absolutely no funding for humanities, and that's just kind of a let's say an outcropping of the materialistic view that is prevalent today, right? So there's no income from doing humanities. I would say it behooves us in the science community to actually pay for them, in a sense. And so if we can find a fiscal structure that balances that out, it would be good. If we can,
I'll tell you a university funding secret. We do pay for them.
yeah, I know, but obviously not enough, because tenure positions become more and more sparse.
Crisis in humanities is an interesting problem. It's driven partly by that, somewhat by student enrollments,
yep,
which are way, way down, right? They've been down by factor 2, and applications are down. This is, but that's a problem. But outside the scope, I think, mostly of this discussion, we should probably stick with cosmology.
Right.
Solving the problems of cosmology or the sociology of cosmology.
But I think one way to address which people get funding and to make sure that big ideas and inspirational ideas get funding is to actually involve people from the humanities in those selection committees, because they know how to let's put it this way, they make their bread by dreaming, in a sense, and we make our bread by having both feet on the ground. So if we can balance that out, it might contribute. I don't know. I'm just spitballing here.
Yeah, so there's been some actually interesting studies on reviews, not bringing in people from the humanities, but looking at the composition of the review committee versus the level of risk that you allow. And the closer people are to the projects, the less risk they allow. So this was actually done mostly in the medical areas. There was a big NIH study. But high-risk projects tend to be rejected by experts who see the risk and see things as less developed. I was part of a very interesting review. I had a conversation about this with Tom Zabrukin, who's the head of NASA Science, a couple years ago. You know, that led to a conversation we had. We had lunch right here with Daniel Kahneman, mm-hmm. who thought a lot about evaluations. And we then, this led Thomas to set up a review, which was called High Risk, High Return Review. These were all proposals that were rejected by the review committees, and they gave them a second chance. And I got to be one of the reviewers, and it was really broad. So we were looking at proposals from earth science and planetary and helio, and I was one of 2 astrophysicists on the review. And most of the things that we were looking at were accretion disk physics, things that were outside of my core expertise. And, you know, you see lots of proposals where people are wrote things that were, because you had the review comments, either missed a few keywords because they were outsiders, a few, you know, and then got a very good instead of an excellent as they looked to mark them down, or sometimes just challenged standard ideas in ways that didn't excite the reviewers. And we ended up funding a bunch of them. And it's an interesting model to think about. I don't know if we want to, I mean, be interested in the views of humanists, but I think even bringing in people from across physics, across the natural sciences and into engineering, we would learn, they would learn to think more broadly.
I would like to say that in Europe we have these ERCs grants, and I think this is defined like high risk, high reward. And I think they tend to only give this grant to projects that are very, very ambitious, but also very, very risky. So, and I think it has been working very well in Europe.
I have to say, and I know David is very familiar with this problem as well, that in the US, it doesn't help when the success rates for things like ATP have been 15% over the last decade. So, you know, each panel can maybe select one proposal. So, you know, there have been studies that show that then you're going to pick the safe option, right? So just having more funding would certainly help.
Problem is we don't have good reviewers too. I mean, you might say that the treatment experts, they don't want risky ones, but everyone's applying, everyone good and active applying. So everyone's applying can't review. So there's a bit of that.
Yeah, it's certainly an issue, and and the people, all our times are stretched, and it's difficult to make time for something that is not rewarded, right? And important for the structure of science, but not.
In ATP, actually, now they're letting people review who are also proposing to that cycle because of this problem. And now that they do it every 2 years, basically every theoretical astrophysicist in the United States applies every single time. And so they have to let the people proposing also do the reviews.
Yeah.
Yeah.
I mean,
obviously not of your own proposal.
Yeah, though some of you who have heard this from me before, but if you're a postdoc about to get a faculty job or applying, volunteer to review, because you're not you'll learn a tremendous amount. And I see a few people who've done it nodding, just how valuable it is. And that's one thing that we could all do that really helps the field. Julia. Yep.
You're very provocative by saying that cosmology is in a crisis, and then you conveniently blamed it on the academic structure in part. Now, if you blame it on that structure, you should probably go further and say all of science is in a crisis, all of humanity is in a crisis, social science. Would you go that far, or is that specific to cosmology? Is there anything in cosmology that makes it more of a crisis than all of these other fields?
In a way, some ways we are, some of these systematic problems are generic to science. Some of the specific things to cosmology, we have this sort of good news, bad news looking at the next decade. I think mostly good news, but I think it drives us to this intellectual conservatism of having enormous amount of data come in. So, this is in a way in which I think we're very fortunate compared to our humanities colleagues, where it's not clear they will have more data, new things to do, that the field will look different in a decade. I think we know that there's so much data coming in from these big surveys that the field will advance. But I think the risk I see is with all this data and the desire to now analyze it, we're developing kind of a project management mentality that there's like really well-defined goals that we have to meet, and people are being funded to meet specific targets and goals. And some of that's the Department of Energy and NASA entering in as big funders, and that's their culture, is to be, for big projects, to be driven that way. So I think that's a particular cosmological challenge for the cultural cosmology, is how do we handle this new data? Do we handle it in the, there's a tendency to handle it in the most conservative way because people have project goals. I've been in enough of these NASA meetings where people just want to, the project managers and the leaders want to make sure you achieve your goals. So everyone's really narrow and encourages narrowness. So I think that part of it exacerbates some of these broader problems. But in most ways, when we're fortunate, but that's thinking about cosmology. That's the distinctive challenge I see.
Could I add to that, like the difference between cosmology and other sciences? So I was for a while in a sort of interdisciplinary institute. So I saw your colleagues in various other areas of science, and astrophysics and physics in general. The funding is much tighter than in other fields compared to the number of people in it. So, I think the grant success rate being so low and sort of the number of faculty jobs being so low advertised every year, except compared to the number of postdocs, I think it's worse in sort of astrophysics and physics compared to most of the other scientific fields. So that's that certainly makes, I think, the field a bit more unhealthy in general. Yeah, the other thing is that David was talking about is, focus on sort of specific tasks, and that's certainly been my experience. For example, applying for grants in which the reviewer doesn't even comment on what I said, was proposing to do, but it was like, oh, the only important problem is a covariance matrix, and you don't do, it was, and so that's a problem that we have, but those reviewers are colleagues, so it's like kind of. I don't know. Anyway, but I guess a general question is now the field is kind of having, with decadal survey and SNOMAS and P5, etc. So is having this kind of big reviews that are kind of, everybody participates. And the question is how do some of these ideas that some of this discussion make it into SNOMAS, for example, or because that will inform the funding agencies, right? The DOE will go, we won't fund you to do this new idea because it's not in the P5 report or something, and so how do we make sure that it goes in there?
So one of my concerns, I don't know what's in the decadal report, so I can say this. Even though I've chaired one of those committees, I look at the funding in NSF astronomy, and we spend so much more on big projects than any other part of NSF. So much goes to hardware, and a much smaller fraction goes to funding individuals, right? And that's a choice the community has made. And I think this is, as one goes into the P5 process and things, we're thinking about that. I completely agree with what you and Rachel said about when money gets tight, we get conservative. But we've made money tight by being, our funding level is actually, it's always nice to have more money, but funding per astronomer or funding per astrophysicist is actually quite good. But we're spending it all on big projects. We're about to ask for we as astronomy community, to fund probably 2 large, big optical ground-based telescopes that cost billions of dollars. One, if we were taking a fraction of that money and putting it into people, we would likely enable a lot more in terms of scientific advance. But that's a choice that we have to make, and we'll see. There's a tendency to go for the big things, but we'll see what happens.
So far, we've kind of addressed the let's say structural part of it, and we could go all day, all of us, I think, here, crying, we need more funding, we need a change in fundamentals, let's say leadership structure. But I feel at least compelled to say that part of it is on us. I mean, so as scientists, we have that in our culture to doubt everything. We should doubt everything, right? Unless it has compelling evidence. And sometimes I think that we don't do that enough. And I think that we should cultivate a culture of having kooky ideas that even some that we really don't believe in. And a good, for instance, is Steinhardt proposed, right, the between two brain inflation that he admitted himself was not a great alternative to inflation. And now he's valiant proponent of the bounce idea, which not a lot of people believe in. But still, these are ideas that are out there. They should be researched. They should be addressed, even as alternatives to whatever it is that we think that we know. And so I think it's largely on us, the younger, I'm not so young, but the younger generation, to come up with ideas which are, half-baked and even, borderline crazy. And I think, and if I were to ask my PI or my boss for anything in terms of support, is to enable me to do that. Like give me the freedom to put some time into some odd ideas. And so, yeah.
Well, we'll claim that Simon's Foundation is actually funding Steinhardt's work. We're the source of funding on that. Let me turn this to a different part, which is the questions. And I think one of the things we want to do is think about what are new questions we want to ask. And I'd be eager to think, now that people have spent a couple of days thinking about cosmology from the perspective of machine learning, what are some of the questions that come to you about cosmology? And I'll give an example of one that I've thought some about, which is if I were to, this is something Paco and I have talked about, right? If I knew everything about where the dark matter is today, does that determine the properties of galaxies? Or does history matter? If I train a network, what do I need to train a network on to predict properties today? Is it the whole history of the evolution of the universe? Or is all the information contained in what we observe today? A lot of what we do in analyses where we talk about things like bias, right, and all those, it starts with the notion that all the information we have today is what we need. So, what do we want to train? What is, if we're going to predict things, what do we need to make those predictions? And to me, one of the really interesting things about the machine learning is it makes you think about what do you train on, what are you trying to predict, forcing a certain clarity in how one formulates the questions. So I have found that stimulating for me. The other people have questions that have occurred to them about how they want to think about cosmology from thinking about it from this machine links with machine learning and so on.
Let me be provocative. So what happens if someone can say, let's try to do some research on Mond or F of R, one of these a little bit strange theories. Should we go through it, or should we stick just to the standard Landau-Koldar-Martel model?
I think we should think about alternative gravity models. Mond has never been my favorite because it's been ruled out in many ways. But I think F of R models are kind of the effective gravity models, I think are all worth considering. It's those ideas, I think, are at the moment at the stage where more work needs to be done on basic theory than on detailed simulation comparison. So I wouldn't be too excited about large numerical simulations of a theory that hasn't been worked out in the, do the perturbation theory, do the analytical stuff first. Would be, like if you're asking, should you do Mond? I wouldn't encourage it numerically, but thinking about its implications is always worth doing. And I think with Lambda CDM, one of the really interesting questions is, can you break it? And how do we break it? And how do we, and a lot of that means understanding the baryon physics well enough to know when it doesn't work.
My impression, a bit on the side of this field is that there isn't actually a shortage of ideas for things like what is dark matter, right? There's this whole sort of landscape of cold dark matter now. It's not just a theory, it's a landscape of theories. But that's almost the problem, is that it's so broad that how do you know, which theories to really work out in detail? And then, as you point out, there's this degeneracy with the baryonic physics, which we don't understand very well. So maybe it's not a problem of lack of ideas, but sort of lack of clues for which ideas should be taken to the next level of testing. And how do you test them, right? How do you rule out theories?
Go ahead.
That are related to the kind of things like using self-organizing map for. It's like, given the amazing data we have, it's like what's the direction? Is there a lack in theory space even? Like maybe there is some theories we haven't think about, but we can actually access with the data. And I agree as well that actually I think we should also really like enjoy the fact that I think that it's a cosmology golden age at the moment, not necessarily a crisis. I mean, it's amazing the kind of questions that we answer and that we can explain to the public, and like people are like really, into it. And I think in like 20 years, it won't be like that. Because we will have measure W and we will measure it to be -1 very precisely. And then like, how do we get, I mean, yeah, the questions will be very different. And I think they will be, as you were saying, related to connection with astrophysics. Yeah, so maybe cosmology will shift to like astro-cosmology. Yeah.
All right, yeah, I don't know anything about anything, but I have the feeling that I did push the button. I did do that, yeah. But I feel like one of the issues that I've personally encountered as someone who's trying to sort of do a little bit of galaxy formation, just to some extent, and apply that to cosmology, is that there is a little bit of a divide between a lot of the fields. I think that galaxy people don't tend to go to cosmology groups, group meetings, and vice versa. And I think that both of these groups actually will often be pursuing the same question, but asking it slightly differently and sort of approaching it slightly differently. So, and that also goes for, high energy physics and cosmology and like X-ray, cluster analysis and all of that. And so, I think that right now there is machine learning and cosmology synergies. And of course, there have historically been other synergies too, but I think that with all of these amazing data and all of that, I think we can take advantage of that even more and combine these ideas more. That wasn't a very good punchline, but I was trying to go for, let's work together.
Yeah. But that's good.
Group meetings, yeah.
Yeah. Yeah.
So going back to dark matter, right? I think it's true that there's a lot of ideas out there, but what's funded is extremely. I mean, at least what I see, in high energy or at the edge between high energy and cosmology, is that until like 2 or 3 years ago, to get a faculty job in particle physics, you need to work on WIMPs, right? And everybody was 100% sure that it's WIMPs, right? And now everybody is 100% sure it's axions, right? And now to get, I sat on committees now, and now if you want to get a job in particle physics, you have to do axions, right? There's no value put in sort of diversification of ideas or diversification of experiments. We have like 30 very similar experiments that look at the same thing and not a wide variety and a wide portfolio. And when we don't have, I don't know. I mean, okay, axions, you can say that they are well motivated, but why weren't you saying that like 5 years ago, 10 years ago, And yeah, that's.
MEV scale axions are well motivated. just ruled out for about 30 years. Yeah, sorry, but I couldn't behind.
Yeah, so I wanted to, I guess, echo what Boriana was saying. I think not in terms of just like cross collaboration between like high energy or like other fields with cosmology, but I think what came up before was that like there are, for example, like so many theories that try to like explain the same phenomena. So as in like a person like who mostly works on data and does like observational cosmology, sometimes it can be difficult that okay, there are these 10 different models of like theories of gravity or 10 different models of like dark energy. Which sort of like paper do I read? Like how much do I focus on like doing the kind of like the background literature and then actually deciding that where do I spend my time as an early career scientist? Because I have to, at the end of the day, the system is I have to be able to like publish interesting work for others. So what's the balance? And I think in terms of like the solution aspect, I did like find this conference, for example, pretty engaging in that I don't do machine learning, but I think the talks were very informative in at least like educating myself with like the basics, or at least like seeing that okay, like that's the way like people who are more interested in that kind of world are like thinking about the problems this way. So perhaps like even in cosmology, like if we were to have, I don't know, like a theory conference for data people or data conference like for theory, like the other way around, so we can kind of like help each other understand like what are the motivations behind the way we are thinking in a certain way. I think could at least like with the early career people kind of like get like a knowledge boost in terms of like yeah how everyone else is thinking about this.
Completely agree with you and Oriana. I mean, this is why I think it's so important that we're back together again, right? And that we see each other, and we, people who think primarily about galaxies go to cosmology sessions and talk to their, have lunch with their colleagues doing that, and and better yet, even sometimes wander down to the physics department and hear what they're thinking about and what those questions are. Because I think it's those conversations that to me will draw, give us the ideas that will drive the field, give us the ideas that will let us look at data in new ways. So I think it's this, restarting conversations to me is, since to go back to our assigned topic of post-pandemic, is I think essential for making progress.
Couple of things. So first off, question for you, I guess, right? So you have on the third and fourth floor, you have your maths, you have then you have your astronomy or astrophysics, you have your biology, and then you have your quantum computing, right?
And neuroscience across the street.
Right. Them I don't know about. That's just what I read on the sign, right? Do you guys have collaborations in the sense that a joint seminar, whatever? Because my experience is that ideas tend to flow from one field to another. That's one thing. And then a remark regarding, I think us, specifically applicable to me, is that we never know what the future holds, so we might as well do whatever it is that we're passionate about. So if the industry goes the Axion way, okay, so what? So they're going the Axion way, and they want to do Mond, and they want to do this and that. If you're passionate about something, then do that. And worst comes to worst, you'll find yourself in the industry. You'll make much more money. Right? It's the cobbler thing with Einstein. But specifically regarding frameworks and tools, I think that maybe we're on the verge of addressing inverse problems in a much more efficient way. So inverse problems are notoriously hard because basically you have to decompose statistical quantities into initial conditions, which is very, very hard. However, the processes that do that in terms of the forward problem are almost always highly nonlinear or even chaotic, dare I say, right? And so if we learn anything from chaos theory via the Lyapunov exponents and all that stuff, is that we tend to lose information because we can't track it. However, if we have the power of neural networks, maybe we can at least approach trying to track things and learn how to do the inverse problem.
Now, first, just in Flatiron, one of the things we try to do is actually talk across centers. And I think that takes the form of, we have one set of good coffee machines, which is very valuable. But probably more importantly in this area, and this is something, and credit Shirley for, is she's run this really excellent machine learning seminars, which have brought people across fields. And the problem you mentioned of inverse problems is a really common set of problems. You have big data, you have inverse problems to solve. And I think that the possibility of solving them with forward modeling, likelihood-free inference, and techniques like that is really promising. To me, that's a new set of tools we haven't had before. And, you know, one of the things when I was a postdoc, working with John Bacall, he had a sign on his door from Hans Bethe that said, only work on problems where you have an unfair advantage. And, you know, I talked to John about what this meant, and he took it as like, you've come at a problem that other people have been working on for a long time. And a bunch of these cosmology problems are things we've been working for a long time. And if you approach them with a new idea, because your particle physics colleague gives you a new suggestion on things to think about, or a new set of data, or a new tool. And for me, what's very exciting about machine learning is it's providing us new tools that let us do forward modeling, that let us work on a set of problems we couldn't work on before. And whenever you have a new tool, you have an unfair advantage. And if you're coming at these problems and are one of the first people to apply things you learn from you know, your machine learning colleagues to problems in physics, you'll have a bigger impact just because you're kind of getting there and doing new things. I mean, I know in my career I've been lucky in that I was very early in being an astronomer who learned some particle physics to apply it, and then lucky in being someone who learned things like Monte Carlo Markov chain and applied statistics at a time which people hadn't done that before. And they, you know, in a way, it was just not knowing. And it's not that one learned things that weren't known, but there were things that weren't known in one's field. And if you come in with a new set of tools, there are opportunities. And I think that's one of the opportunities right now at the moment. Other thoughts? Yeah.
To bounce back on the fact that in observational cosmology, like current analysis, it can take a very long time, which, like, for instance, for testing modified gravity with, or like beyond lambda CDM, it took like 4 years within GS, which I would not recommend if you're a general scientist. So that's where I think machine learning is really promising, is to be able to accelerate the pipeline or like help making this process faster. But I'm actually not even sure that will be the case. I think it will be the case if we have tools that are like ready to use, kind of, which is very difficult, as we talked about yesterday, to make the tools like adaptable to like specific cases. So yeah.
So I just want to mention one of the feeling I feel in these days, kind of the improvement of simulation speed seemed to be very exciting to me. And that kind of reminds me of the fast Fourier transform algorithm. Kind of the idea is that if you can really dramatically increase the speed, that means there's some intrinsic simplicity or structure in this question. And because you found that structure, you kind of save the computing power. So I think it'll be really interesting to see whether finally we can realize some of the intrinsic simplicity in the equation of like either gravity or in some other field like turbulence, which the machine learning tools found for us.
When you mentioned Fourier transforms, it reminds me of a story that, career path of my undergraduate office mate, who, after getting her degree in astrophysics, went into cardiology. And what she told me was she ended up, becoming a professor at University of Arizona. She said, I knew this thing called the fast Fourier transform that people hadn't applied before to cardiographs, right? And I think it's one of those things where it's like, right, we were talking about this years ago. It's like, to us, it's obvious. You have a time series, you take a Fourier transform. That's why I think it's really important to have conversations, to go back like this. It's, you come in with these new tools, you talk to people who will ask questions that you either ask them or they ask them of you that are stimulate new work. And that's where I think can be very important.
David, I think an important question is, does the power spectrum of your heart contain all the information? Sorry, we have been discussing this during the meeting.
State of one's heart.
I mean, I guess you take your beats from your heart. I guess you can compute the power spectrum or something.
Yeah.
Does it contain all the information? Can we fully describe our heart with that?
No. No, I think I actually know enough about that the phases matter. And it's not just the power, it's phase problems. And a lot of heart problems are associated with mode coupling and the phase information that it tells you about what's going on with mode coupling is telling you a lot about the dynamics. Yes. Right. Yeah, exactly. It resets things get phase locked and you reset the phases. And it's so I think it is very much something where there's more information than the power spectrum. More information than just the initial conditions. On that, why don't we thank everyone for the discussion. Hope we didn't ramble too much, and